Okay, so we're at the point here where moving on now to other forms of the radiation hardening. I mentioned that just briefly, and I see that this does not work. I see, oh, there. It doesn't work with the pointer. This is off the internet, and this is some work by Briseno and Ian Robinson's group, showing the effect of how dislocations glide in an unirradiated case. But then if you irradiate it, I can't go back there. If you irradiate it, basically it's more difficult for the dislocations to glide. In that example, I've just flipped through. I apologize, but I can't go back when I'm recording. In that example, and you can see it on the internet, very, very little damage, radiation damage, but what little damage there was albeit submicroscopic, was still sufficient to drastically slow down the dislocations, the dislocation slip. So having radiation damage is basically one way to harden the material, make it more difficult to get dislocation slip. But irradiating doesn't necessarily give you that damage increase in the defect density, because if the temperature is low enough in nickel alloys and austenitic steels, you can get to a condition where recombination is enhanced, and basically there is insufficient supersaturation to get cluster formation, and the material is basically remains soft at the lower temperature. Again, a little bit of counterintuitive, but that is not the reason for the change that we see in irradiation. But it just illustrates that the general softening of material at lower temperatures occurs for two reasons. One, because it's easier to dissolve and disperse the precipitates, but also you don't get the hardening effect if it's at low enough temperature. So going back to zircaloy now, I apologize for flipping back between different alloys, but some of the mechanisms, or many of the mechanisms, are very common to both, so it doesn't really matter. So when it comes to radiation hardening, this is the typical way that material is hardened. You create dislocation loops and then barriers for slip. In the case of zirconium, you also, quite apart from the deformation producing two types of dislocations, radiation also produces two types of dislocations, and typically that's dislocation loops, prismatic dislocations on a basal plane compared to the prism planes. Oh, and I just throwing this in just to illustrate a little video I took when I was a student doing my PhD of a C component loop in zirconium in the high voltage electron microscope. So we're using the electrons to image the material and at the same time damaging the material, creating point defects at an elevated temperature, 300 degrees C in this particular case. And you can see how the loop is growing and how other defects are produced. The interesting thing about C-component loops in zirconium alloys is not only are they barriers to slip, but they have an effect on the dislocations directly, because the C+A dislocations I mentioned earlier, they will attract vacancies. Oh, sorry. What you tend to get is vacancies tend to agglomerate on these dislocations and climb helically. And what that looks like, if you look at a before and an after, if you have a screw C+A dislocation and then you irradiate it, you get this helical climb. And we're seeing the helices edge on here, this helical climb. And basically what that does is that it basically that locks up this dislocation. I mean, that's a very severe hardening effect, because that dislocation is not going to go anywhere. Here's another example of the complexity of damage of dislocation structures in materials, but also when you irradiate. So in the berserk niobium pressure tubes, which I'm most familiar with, you have this small grain, high dislocation density structure, and then when you irradiate it, it just becomes even worse, because you're introducing all of these dislocation loops. And then when you look at the C component structure, which can be very complex, even more complex when you irradiate it, and it all goes to the same end. It's just you basically harden the material, makes it much more difficult to do. So in this is back to front, but what I wanted to show is that the loop damage, this is the A-type loop damage now, in a berserk 2.5 niobium pressure tube. The density of the damage varies according to the temperature and the flux profile. So we tend to have a distribution of damage along the length of a 6-meter long tube, going from the inlet here, I'll get the pointer again, going from the inlet here to the outlet here. And at the cooler end, you tend to get higher density of radiation damage and a lower density at the hotter end. These values here for the damage density are taken at different clock positions, starting from at 6 o'clock, which is at the bottom here, and 12 o'clock at the top. And what that basically means is, as you go from one end of the tube to the other, the spread in the conditions around the tube increases, and the tube gets cooler at the top and hotter at the bottom, and that's reflected in the damage density. And that's what's phenomenon known as flow bypass, and that's subject of another talk if it ever came to that. So this just illustrates the general effect of temperature in the berserk niobium pressure tubes on the damage density. And this is illustrated also in steels. Here's something I took from a review by Powell with Steve Zinkel. And basically, you see, as a function of temperature, using yield strength as a surrogate for the loop density, what you see is that at high temperatures, basically the loop density becomes much lower, and the irradiated material, the yield strength of the irradiated material approaches that of the unirradiated material, and that's because you have insufficient supersaturation at the higher temperatures to cause loop formation. There's a sweet spot here around about 300 degrees C, and at lower temperatures, because you get a bit more recombination going on, you can reduce this density as well. And again, that's counterintuitive, but not if you work with radiation effects and what the supersaturation of the point defects means when you do rate theory calculations. And the last slide for this session is here, and it's just a copy of a figure from work by Sak Byun, who did some excellent work on strain localization, mechanical properties of irradiated steels, and he's mapped out the how the what types of deformation one gets as a function of the stress and as a function of the dose in different material, not in different materials, in 316 stainless steel. This is a low temperature radiation. So I mentioned that in the austenitic stainless, in the Inconel X750, at this temperature, actually we didn't get any damage, but it seems that in 316 stainless steel you do. So I'm not sure why we get that difference, but it's still diminished relative to the 300 degrees C. So even though we have a lower damage density at these temperatures, you can map out what type of deformation mechanisms apply at different regimes as a function of dose and as a function of the stress. What was interesting and worthwhile noting in Björn's work is that they found that in radiated material, they found that twinning occurs at a lower stress than channeling. And I haven't talked about channeling, but I will. That's going to be the main part of this talk, in fact. So, but just pay attention to note that Björn's results showed that in irradiated materials, irradiated 316 stainless steel, typically they would observe twinning at 600 MPa and channeling at 640 MPa if they were to demarcate the two. Although by and large, they often got both mechanisms occurring. Okay, so I'm going to stop.